My name is Tom Brown, and I'd like to present some work with colleagues at KAT and Aarhus University looking at the effects of low acceptance for grid expansion and onshore wind on climate-neutral energy scenarios for Europe. For this purpose, we're using the open model Pipes Europe SEC, which is available on this GitHub link, and we have here all the sectors relevant for net zero. So on the demand side, electricity, heating, transport and industry, where we're covering steel, cement, chemicals as well as their feedstocks, and then all the different ways of meeting that demand with electricity, hydrogen, methane, liquid hydrocarbons, and so on. So we have to be very careful here, of course, with the carbon dioxide management. So we have carbon capture and usage and sequestration, as well as direct capture from the air. Because we need a high spatial and temporal resolution to capture the effects of grid bottlenecks and wind and solar, we have a high resolution model here, as we know that these bottlenecks exist already today in today's system. We cluster this grid model down to about 181 nodes, which is still enough to capture those bottlenecks. We look at all of those energy sectors and reduce CO2 emissions to net zero. We have smaller bidding zones and widespread dynamic pricing. We use conservative technology assumptions predicted for 2030, even though we expect to reach net zero sometime between 2040 and 2050 if we're lucky. We examine then the effects of low acceptance and low levels of grid expansion onshore wind on the costs and the technology mix. Here's an example of the investments in a simulation where we only allowed the existing grid to be used. We have no grid expansion, and you see a lot of solar in yellow in the south, a lot of wind. Offshore wind is lighter and onshore wind is darker, clustered around the North Sea where the resources are good, and lots of power to gas and power to liquid being used to soak up the excess energy. When we have some grid expansion, something similar to the 10-year network development plan, then we see grid built out around the North Sea to balance those big weather systems coming in from the Atlantic and smoothing them over the north of Europe. So if we examine how the total system costs, these yearly system costs behave as we expand the grid from 1, which is today's grid, to 2, which is a doubling of grid, we see that the costs reduce significantly when we allow grid expansion, up to 47 billion euros per year, but most of the cost reduction happens in these initial stages, so it's quite non-linear and we get quite a big benefit at the beginning. The overall costs are a little bit higher than today's system is calculated with the same assumptions, which comes out around 700 billion euros. We can do a similar experiment here on the x-axis where we reduce the available onshore wind from the technical potential down to zero and see it get substituted with offshore and solar at not too big a cost penalty of around 42 billion euros. Again, it's non-linear, so we get most of the benefit very early on. What enables these scenarios to work is a new hydrogen network which is built, which takes over a lot of that role of balancing in space and time against the variable renewables.